This work presents a framework to optimize multirotors for particular navigation tasks. First, we define a procedure that can transform a real-valued vector into an airframe. This procedure takes into account fabrication constraints, such that the resulting design contains no unfeasibilities, such as colliding propellers. Then, a reinforcement learning procedure learns to control the design for a particular waypoint navigation task. The average task performance of the design is measured on 20,000 episodes with the trained policy. Based on task performance, the optimization algorithm suggests a new design. The cycle is repeated until the computational budget runs out. We consider two different navigation tasks. Both of them involve mostly forward flight through 0.5 by 0.5 meter waypoints. Task A relates to flying towards a goal while smoothly avoiding obstacles. Waypoints are set to 0.5 meters from each other with some additional lateral offset. Task B refers to agile navigation with last resort obstacle avoidance. Waypoints are placed at 0.25 meters from each other with occasional sharp lateral changes. In both cases, task performance is measured as the number of waypoints that the airframe crosses in 5 seconds. It is important to note that different waypoints are sampled randomly from these specific distributions each time. In the following, we show the results of the 3 experiments carried out in the paper. In the first experiment, we optimized the multirotor design for Task A. The video shows how task performance increases with the number of evaluations. First, we use Bayesian optimization to perform global optimization. This is followed by covariance matrix adaptation evolution strategy, which further refines the best found solution. Now we compare the optimized drone to see how it performs when compared to the planar design and other fully actuated designs from the literature. Baseline designs have been scaled to match the inertia and mass of the optimized design. The optimized design obtains the best task performance with a lower angular velocity. One of the reasons is that the optimized design has a higher maximal lateral actuation than the rest. In the second experiment, we optimize the multirotor design for Task B. As in the previous experiment, we execute Bayesian optimization followed by covariance matrix adaptation evolution strategy. We compare the optimized drone with the baselines. The optimized drone flies by producing lift with 2 of the motors, with the other 4 motors pointing backwards. This gives the drone a shorter stopping distance and can therefore move faster than the other designs when flying forward. To demonstrate sim-to-real transfer, we build and deploy the multirotor optimized for Task B in the real world. As can be seen in the graphs, the performance in simulation closely matches the real-world performance. This is the top view with an overlay of the waypoints added in rendering.